CLion, a cross-platform IDE for C and C++. Download now.
A compiler in C++. Yeah, let's get started. I'll start with the agenda of the talk. We'll start with the introduction to compiler and then move on to various stages in compiler. Afterwards, we'll learn how I compiled my compiler to webassembly, which allows us to run our compiler in browser, and I'll conclude by uh, talking about the benefits I had by compiling my compiler to webassembly. Yeah, let's begin with introduction to compilers. Basically, a compiler is a translator. What it does is it takes a source program as an input and generates its equivalent target program. Right. For example, a client compiler takes in a C++ program and convert it into a machine language. And another form of compiler could be from, for example, a C++ to C compiler. And we have a term for such compilers, and they are called transpiler, right? But generally, speaking about compilers, the target program is generally machine code, machine language, right? And whenever I talk about compilers, I like to talk something a bit about the other way. That is, can we go from machine language to C++? And the next slide will be about that. Yeah, and the question is, can we go from machine language to C++? I'd like to start with by stating that nothing is impossible, right? And the main problem with machine language is they are very specific to hardware. And another problem with them is they lack high level abstractions. Like they do not have a variable, the concept of a variable name. So we cannot generate 100% same C++ code just by looking into its machine language, because we cannot just tell what the programmer declared, what the programmer declared name of the variable just by looking at machine language, right? So there are other issues as well, but these are the main issues that makes reconstruction difficult. But we have a word for such type of compilers, and we call them the compiler, and they are mostly used in reverse engineering tasks. Yeah, so this is it about the compilers. Now going back, so far what we did is we looked to a compiler mm, as a black box. It just takes in a source program as an input and outputs its equivalent target program, right? Now we will look inside a compiler, and basically the thing is a compiler. The working of compiler is grouped into multiple stages, right? So we will look into each stage now. The first stage is the Alexa. Uh, uh, Basically, what Alexa does is it tokenizes the source code. It tokenizes source code into and returns a sequence of tokens. So what I mean by tokenization is, for example, I have a C++ program here, and if we look at the output of the Alexa, we can see that int here, the first token could be a type, right? This is because int is a type, and the Alexa can group int into a token name of type. And similarly, main with name of function can be tokenized into a token named ID, and then the compiler can proceed in a similar way. Similarly, 5 can be grouped as number, right? This plus is grouped as a token plus. Okay, and this is and the Elixir proceeds. It scans every character in the source code, check if it finds some token, and then just tokenize it and return to the next stage of the compiler. And the main thing to note here is we do not have tokens for comments, because comments have no relation with our target program. because comments are just for programmers. So we just ignore them. And uh, in the other stages of the compiler would also do not need to take care of their comments. Right. Okay. So far what we did is we read the source code and group them into tokens. We and then the legs are just we just return a sequence of tokens that is a vector of tokens. Okay, now let's see how we can define a token for our class. The main thing to look here in, yeah, just to note that this is just a reduced version of the code, so that I could fit in a single slide. Okay, the main thing to look into this is the member variables, line number and column number. So what we do is we keep track of the position of every tokens in our language, in the program, right? And every token has a name, token name. Just what we saw earlier, right? And we have defined a constructor here that just takes in some required values and just initializes the token. Okay, here is how I define the token name. It is defined as an enum class. And what we do here is we group or we just group all the tokens in our language. Yeah. For example, plus the token name plus, it's just a token, just a representation for the plus symbol. Similarly, minus is a representation for minus, and so on. So what we do here, we just list just group all the name of the tokens here. Now, uh, let's see how we can define our Alexa class. The most important thing for Alexa is to scan, right? So here is our scan token function. It will just look into every character in the program, and then just find and sees if it can find a token, right? We'll look into its implementation yeah, later. And another important thing to note here is the token vector. As I mentioned earlier, Lexer returns a sequence of tokens that is a vector, right? So we need some way to store it. We have stored it in a vector of token. Now let us see how we can define the scan token function. Okay, scan token function basically takes in a single character here. And what we do is it's a big sweet case statement, and it just sweeps over those characters. And for example, here if the character is a new line character, right? What we do is we just increment the new line. We increment the line number by one. And similarly, we just set the column to one because we are at the start of the new line, right? And another thing to note here is we do not add this new line character to our token vector. This is because our language do not consider new line as a token. This is it, right? Next, if what if the character is a semicolon? So semicolon, we just add it to our token vector. We increment the column by one, and that's it. Similarly, to handle comments, uh, this is a special case because we do not care what the comment is, right? So whenever we encounter a hashtag, we'll just consume all the characters until we find a new line character, right? And we do not even add anything to the token vector because we do not care what the comments are, right? Uh, now let's look at one of the important concepts in lexical analysis, that is looking ahead. So far, what we did is we looked at single characters like plus or like plus or has, right? But there are other constructs. For example, the symbol greater than or equals to. If we will just look at a single character, we'll never be able to tell that it is greater than or equals to. So for such kind of character, we need to look one step more, right? One step ahead. For example, if we get an greater than symbols, what we will do is we will check if the next character is equals to, right? And if it is equals to, then we are assumed that okay, this is a greater than equals, right? And we add it to the token. But if it isn't, we'll just add, okay, we are convinced that this is just a greater than symbol, so we'll just add it to our token vector. All right. Uh, so far, we grouped the Alexa grouped source code into tokens, and we just store those tokens into a vector, and then we just pass the token to the next stage of the compiler. And the next stage is a parser. The main task of a parser is to check for the syntax of the program, right? Well, what the parser does is it looks at the sequence of token written by the Alexa, and then check if the if the sequence of token matches with our grammar. And if it doesn't match, it's an error. And we can just use the position we store for every tokens to pinpoint the error locations, right? And uh, now let us see how we can check for syntax of a variable declaration, right? Okay. Let's now think about how would we meet graph for a variable declaration, right? Okay. What we decided is, okay, let's make variable declaration start with the word let, and then the name of the identifier. For example, let x would be a correct syntax for variable declaration, right? Now let us see how we can do this. The parser will look into the sequence of tokens it receives from the Alexa, and whenever it sees the let keyword, right, it will just move to the next token, and it will check if the next token is an identifier. If it is, we are done, right? Because we found an let, we found an identifier. So the parse is successful, and we have assured that okay, this is a variable declaration, right? Similarly to parse variable assignment, what we do is we look if it is an identifier at the beginning, and then we look if it is an equals to symbol, and then we'll just parse anything that's on the other side of the equals to. And this is how we can just parse variable assignment. Similarly, well, we can parse function definition. It's similar to what we saw earlier. We will see if it starts with a function keyword, and then check if there is a function that is an identifier, and we will just see if we have an open parenthesis next. This is the right place to check for the parameters of function, uh, and then we will just see if there is a closing parenthesis. And in the similar, we will just proceed ahead, and we'll just check if we get if the sequence we receive from the Alexa is matching with the syntax or matching with our grammar. Okay. Uh, yeah, so we'll just proceed forward in similar fashion for every grammar in the language. I have utilized a commonly used technique, recursive recent parsing for in my project, and in fact, recursive recent parsing is heavily used by GCC compilers. Yeah, so this is an interesting technique, but I won't talk about this in this talk. Okay, so far what we learned is the Alexa return sequence of tokens, right? But what should a parser return? Uh, a parser, a parser would return. Uh, there are lots of things we can return, but one other thing we can return is an abstract syntax tree. What if abstract syntax tree or AST does is they just capture the structured notion of the source code, and the notion is the structured notion somewhat easier for the other stages of the compiler to process. We'll see how. Okay, for example, I have a similar program on the right side, and it's AST for on the left side. Here, what the program has is it has main function that has a declaration and if statement within it, right? So what we do is we define a main function, a node for the function main, and anything in all of its children. are the body of function. And if you look into this branch, right, what we have here is a node for variable name and a node for a constant value and a node for an operator that is equals to. So if you look into this carefully, what we see is this is an equivalent to x equals to 5, right? So this is so the statement x equals to 5 can be represented this way. Similarly, on our right side, on the right side of the main function, uh, what we have is if node, and the if node has a children for the condition and the body of the node, right? This is how we can represent an AST for the program on the right. Okay, let's see now how we can define a class for AST. And that is for variable declaration, right? The only thing that matters for a variable declaration is the type name and the variable name, right? Uh, so this is what our member variables will represent, and we have a constructor that just takes in those value, and we are going to initialize AST. Similarly, if you look into if statement, what we need to know is the condition of the if and the body. Right, this is what the AST needs to take care of. Okay, if you look carefully, all the for example, in the for the if statement, all the stages of a compiler do not need to worry whether there is an if whether there is an if keyword followed by an open parenthesis and then a condition inside it. It doesn't need to take care of all the syntactic structure because those are already checked by the parser, right? So what AST does is it just omits the syntactic structure and returns and it just omits the syntactic structure, and so that it is easier for all the stages of the compiler to proceed ahead. And it also makes life easier for the semantic analyzer. We will see it later. But now what we will do is we'll update the function, our parsing function, so that our parser would return an AST now. Okay, here's the same function we saw earlier, but we have changed the return type to variable declaration AST. The logic is the same. We'll look if it is late keyword first, and then we'll see if there's a variable name, and then we will see if there's a colon at the end, right? If everything is fine, we'll just return a variable declaration AST. But if we encounter a late keyword at the beginning, but we do not see an identifier, we know that this is an error because the syntax doesn't match with our grammar, right? So we can throw errors. And one good thing here is, since we know where the token is from its line number and column number, we can just pinpoint or we can just pinpoint the position and say something like missing a variable name for the date statement or something like that, and just pinpoint the error location, right? Similarly, if we find both late and identify name but do not find a semicolon, we can just say missing a semicolon here at this line number, or we can uh, uh, report some good error messages to the program. Okay, the updated function now returns AST. That's it. It returns an optional value, right? And we and also note the use of unique pointer and C++. Now we'll do the next stage, that is semantic analysis. What semantic analysis does is it checks for the meaning of code. What this means is, let's say we have an integer variable x and we assign a string to it, right? That is syntactically correct because what our syntax expected was identify name and equals to operator and then expression, right? But the meaning here is not correct because we cannot assign a string to an int. So this is where semantic analysis comes in. And yeah, as I talked earlier, semantic analysis, one example is type checking. Another example could be to check whether the variable we refer belongs to the current scope or is reachable from the position where we are currently in or not, right? Uh, Now we'll see how we can manage scope in our language. Okay. Uh, there are different ways how we can implement this, but I used I use a linked list to implement this scope. One of the one of the benefits of using a linked list is can easily capture the notion of this nested scope, right? This because a scope will point to a span scope, and a linked list is a good data structure to represent that. And another thing with scope is every scope has its associated symbol table. What a symbol table does is it stores information required for other stages, right? Required for other stages. Uh, for example, an example of symbol table could be we store the type of every identifier we see in our program, right? Here we just have X, Y, Z, and they just store the symbol table just store the types, right? Uh, Now, if we look into how we can define our scope class, the main thing to notice here is pointer to parent, right? Pointer to our scope, and this is a pointer to its parent. We have a symbol table for every scope, and we have two important member functions: add to symbol table and search to symbol table, right? Now. Let's see how we can add a value to symbol table. So we implemented here symbol table is just a map, right? So we'll just use the insert method, and we'll just insert the key, insert the value into the symbol table. But searching the symbol table gets trickier because we need to look into the parent of the scope as well. So here, what this implementation does is we'll just look for in the current scope at the beginning. If we find the identifier in the current scope, we're happy, we'll just return, right? But if you do not find in the current scope, we will just need to traverse through the linked list until we reach the end of the linked list. And if it is the end and we still do not find the identifier, um, uh, it means that we are trying to refer a variable that's not within our security, that's not traceable from the current scope, and can just throw an error here, right? So this is where this helps us, especially in the case where the scope is nested, which this commonly happens because the scope nested most of the time. Okay. Now another step is to generate intermediate representation. So far what we did is our compiler read the source code, tokenize it, pass it to the parser check for the syntax, we then check for the meaning of the code. Now, what this means is the thing program out there is correct. Now, it's up to the compiler to generate an equivalent program for the programmer, right? Equivalent target program for the programmer. Now, where intermediate representation comes in is it is a representation, but it's not the target code that the programmer wants. It's just a representation uh, that makes easier for the backends, I should say, for the later stages of the compiler to generate target code. IRs, short for intermediate representation, are designed in a way that it is easier to just analyze and optimize them, right? Uh, and I've used LLVM IR for this project. What LLVM IR is it is an intermediate representation used by the LLVM compiler infrastructure. It is highly optimized and portable. Uh, so so it will be kind of easier to target different architectures, right? The main advantage of LLVM IR is what we can do is let's say we have a compiler for C, we have a compiler for Fortran, we have Haskell, compiler for Haskell, and if the front end part of the compiler generates LLVM IR, can use a single LLVM optimizer and generate the target code for different architecture without much of a hassle, right? So you see the reusability here. That's why what we can do is our front end will use generate intermediate representation, that is LLM IR, and can just use optimizer to target multiple architecture. So this makes our life easier. Uh, uh, so this is one reason I used LLM. Okay, now let us see how we can generate IR for the variable declaration. Uh, okay, how we will generate variable declaration is LLVM. Okay, to generate variable declaration, what we can do is we will see if the variable is currently if the variable is currently in the current scope or not. If the variable is already defined, because that's an error, right? So we will just see if we'll just say if the variable is present in the current scope. If it is, it's a good time to throw an error. But if it isn't, we'll just use a function. This is a function provided by create alloc is a function provided by LLVM, and it just generates an instruction to allocate memory for the variable, right? And this is how easy LLVM does for us. Similarly, if you look at the generate IR function for our function definition, what we'll do is we'll just iterate over all the statements in the function body, and we'll call the generate IR function for every statements, and this is how we can generate IR for the function body. Once we have generated an IR, LLVM IR, it's kind of easier for us to generate object code. We can really rely on LLVM optimizer for the rest of the stuffs. Now I won't be talking about generating target code. Rather, I'd like to talk about how I compile the compiler to WebAssembly so that I could run it in a browser, right? Running our compiler in browser. So that's the main target is this. This is a website that has a code editor on the top and a terminal on the bottom, and we have a run code button there. And what I want is the user presses in the run code button and the code compiles on the browser. Right. So far, running a program in browser goes this way. We have a server that has a compiler. With, we just send code to the server. The compiler in the server compiles the code, returns the machine code, and it outputs. And it outputs back to the client, right? But another interesting way and modern way I would say is to use WebAssembly. So what WebAssembly is, it is an assembly-like language, but that runs on web. So basically, it's a language other than HTML, CSS, and JavaScript that runs in browser, right? Since our browser understands WebAssembly, we can just run the compiler in a browser if we are able to compile our compiler to browser. So this is a traditional way, and if we use WebAssembly, we'll just have we just need a client running browser, right? And this is just a traditional way. We don't need no service. Fine. Okay. Now let's see how we can take our compiler to browser. Here is our compiler we just talked earlier. What we'll do is we'll compile our compiler to WebAssembly, and this is the .webassembly format. This is the generated assembly file, right? Assembly file for the compiler. We will just take in the source code, pass the source code to our compiler in .wasm format, and it will just send it out for us. The thing is, we will load the .wasm file into our browser, and we can come then in JavaScript can directly communicate with WASM in the browser itself, and our aim will be achieved. Now, how we can compile to WebAssembly? We have a compiler that is in C++. Now we need a compiler that convert C++ to WebAssembly, and we have such compilers, and one of them is EM scripted, right? For example, we have a simple main.cpp file and we want to convert it to WebAssembly. What we can do is we can use EM scripting to compile, and it just outputs two files, generally a JS and version file. Version is short for WebAssembly, and main.js is just a glue code for the version file, right? And okay, now the user will type in code in the editor, and when the user presses the output button, the code in the editor should be passed to our compiler. That's the main aim, right? Okay, to do so, we will slightly tweak our compiler. We'll define a compile program function that takes in our source code. So what we're gonna do is we're gonna expose this function to JavaScript, and this function basically just performs the whole compiler workflow. Uh, and what we're gonna do is we're gonna expose this compile program function to JavaScript. How we can do that? How we can do that is we will just wrap this into we'll just wrap this into first this em scripting macro, and uh, while building, what we will do is we will use this export function command that exports underscore compile underscore program. And what this does is it makes compiled program accessible to the script, right? Uh, now, how we can call that compiled program first from JavaScript, right? So this is just normal JavaScript flow. We get the read the value from the code editor, uh, and we do some stuff here. We just read we just create some buffer for us, and what we do is we'll just call this compiled program function that we exported earlier from using EM scripting, right? And we just pass in the pointer to it, and that's it. And this is just malloc free. We will listen. And the what this one the main thing is this is called the compile program. So what this does is it calls the compile program we defined earlier, and that compile program function calls the elixir parser, all the compiler workflow that we need, right? So this makes all life a lot easier for us to run to test our compiler in the browser directly. Okay, now we're at the end of the we're at the end. So I'd like to conclude by talking of some benefits by what I achieved by compiling this compiler to WebAssembly. The main one of the good advantages was that I would implement a feature, and I'd compile it to WebAssembly and load it in the browser, and I could just check my features in better UI. Yeah, I could pass it to my friends. Say, hey, look, can you just find bug in my this feature? And things like that, right? And another thing is, it was slight kind of easier for me to find some bugs by checking it in the browser. This is because WebAssembly has a very limited runtime, very limited memory, and therefore the main thing is out of bounds error were easier to check, because generally when you run in native execution, those error won't crash the program. But when I ran it in browser, and if I had once a error, it would crash my entire program, right? So this is how compiling to WebAssembly helped me. Uh, yeah, this is it for the talk. Thank you very much for being here, and I hope you enjoyed the talk. Thank you.